Okay, maybe a pop quiz. Okay, you may recall last time I had asked you to think about why we have such a range from low to high porosity and hydraulic conductivity for limestone. Anybody want to tell me why?
There's different variations of limestone.
Well, there are, but it's even more specific than that. It's a good start. It's not just how the limestone was deposited. Yes, ma'am.
You mentioned in the class how clay kind of, when it forms, it leaves more pores behind, and like the crystals seem to cement everything together.
Again, you're nibbling around the edge of the question. When we talked about clays, that was originally in the context of siliciclastic sands and sandstones, cements and matrix. I'm thinking something about something that's unique to limestone. What is a property of limestone? First of all, what does limestone consist of? What mineral? Calcite. Okay. What is a unique property of limestone? It dissolves. What has that got to do with porosity or hydraulic conductivity? Lots. So when we look at low porosity of limestone, it's usually low primary porosity. Most limestones, a few exceptions like a coquina, would have a high primary porosity, but most limestones, fine grain, micrite, is basically mudstone. Just happens to be carbonate. So it's going to have a low primary porosity and hydraulic conductivity. On the other hand, start dissolving it, and you got caves. You got huge amounts of porosity and hydraulic conductivity. So limestone very much depends not only on its depositional history, but on its diagenetic history as well. And in reality, all rocks do, but limestone's particularly so. Okay. Well, let's go back to looking at our aquifers, and we've largely been talking about unconfined aquifers, aquifers that are basically exposed to the air, albeit at the water table, and often merge with the stream. But we also have confined aquifers. Now, confined aquifers are separated from the surface by a confining layer. We'll talk more about that confining layer in a moment, but basically it's going to be an impermeable or relatively impermeable unit. So we have water, saturated water, both in a confined aquifer and saturated, let me rephrase that, saturated material. Water is always saturated. Saturated aquifers, both confined and unconfined. Now, the top of the unconfined aquifer is the water table. The water table is the level to which water will rise in a well. It's not actually the top of the saturated zone. We've got that capillary fringe, but it is the top of that portion of the water that will drain. Okay. Now, in this case, the confining layer is clay. And so below here we happen to have a limestone, but it's also saturated. Okay? So if we put a hole down there and we cement it or put some kind of an impermeable sleeve so that we're only drawing water from down here, then that water will also rise to a water level in the well. But that level, the level to which a water rises in a confined aquifer, is in fact the pressure surface, or sometimes called the artesian surface, or the potentiometric surface. All these are names for essentially the level to which water will rise. And in this particular case, you see that it actually rises well above the water that's in the well. And that is because these confined aquifers are under pressure. And the greater the pressure, the higher it'll rise. Think of squeezing a soft drink in a straw. You just squeeze it, it will rise, okay? So we're going to be looking at these various types of aquifers. Now, that confining layer, it typically is called an aquiclude or an aquitard. And basically it's something that's relatively low permeability. Could be a siltstone, shale, a mudstone. There's a lot of different things, even a clay-rich limestone. The distinction is, does it retard the flow, hence aquitard, or exclude flow, hence aquiclude? We used to use the word aquiclude a lot. It turns out all of these things that are confining layers are slightly leaky. And so an aquitard is probably a better word. And it's a good word because it reminds you that it retards but doesn't exclude the flow of water between adjacent aquifers. Okay. Now here it's called an aquitard, and here's the confined aquifer. Okay. And so that water gets there someplace, and of course it stands to reason it does not get through by infiltration here, unlike the overlying aquifer. So it's got to come from somewhere, and it comes from an area we call the recharge zone, which is the area where that particular geologic stratum, that aquifer, is exposed to the surface. It's there and only there that you can actually get water into this confined aquifer. Okay, so it's the area of a confined aquifer where rainfall enters and therefore recharges that aquifer. Okay, that makes it a very special place because it's only here that we can easily contaminate that aquifer. Because here, surface contamination, at least, tends to be separated from that aquifer by the presence of that confining unit. Okay. Now, we've got the level to which water will rise in a well in a confined aquifer, and that's the pressure surface or the potentiometric surface. Okay. And it goes by other names as well. I'll try to stick to these. Okay. If you want to protect a confined aquifer, you need to protect the recharge area. So you see signs all over. Groundwater protection zone. Edwards Aquifer, environmentally sensitive recharge zone. When you drive into central Texas, around Austin, you see signs all over. They're very proud of that zone. They tell you when you're entering it, they tell you when you're in it, and they tell you when you're leaving it. And the reason, of course, is because there's very strict land use controls in that area in order to avoid any kind of surface contamination. Okay. Now, that pressure surface I was talking about, it's pretty easy to visualize if you can just visualize the fact that your water in your house is under pressure. And so when you open the spigot, it sprays up. And the reason it's under pressure is because it's being stored, for the most part, is being stored in a tank. And so the level, oops, I thought I'd done that. Just a second. Nope, sorry. Okay. The level of the water in the water tank represents the maximum potential energy. Okay. And so water could rise up to that point. Now, in reality, it doesn't, because as it flows through the pipes, the water will rise to a surface not quite the same as the elevation in the tank because of resistance and loss of energy because of friction. But nonetheless, that surface represents how high the water could rise, which among other things means if you've got a 5-story building, you're going to have auxiliary pumps because you can't get water to the 5th or 6th floor. Okay, that surface is analogous, in fact it's the same as the surface here, where the elevation of the water table in the recharge zone is analogous to the elevation of the water in your water tank And that level, albeit decreasing with distance because of loss of energy due to frictional attenuation, represents the level to which that water will rise if you put a hole there, a well. Okay, so let's look at 4 different wells. Well 1 is sitting in this aquifer. Here's well 2, well 3, and well 4. Assume for each of these that only the very base of the well is slotted. Okay, so which well is in an unconfined aquifer?
Sandstone.
Give me a number. 3, absolutely, sure. So here's, and what is this surface that I'm drawing? Between the saturated and unsaturated water or material. That's the water table. And this depression is the Kona depression. Okay? All right. Now, in general, we talk about artesian wells as being wells that are tapped in confined aquifers. But we make a distinction between a non-flowing artesian well and a flowing artesian well. A non-flowing artesian well rises to wherever the pressure surface is, but that surface is below the ground. A flowing artesian well is one where the pressure surface is above the ground. What that means is, quite literally, you put a hole in the ground and it starts flowing out to the surface. Okay, so that would be a flowing artesian well. So which of our wells is a non-flowing artesian well? 1, absolutely, because the pressure surface, the water will rise, but not to the surface. So you can see where this is going, which of the wells is a flowing artesian well. Right? No, 2, absolutely, because it's going to try to go all the way up to here. Okay? So this quite literally is a picture of an artesian well flowing. Okay? We also have artesian petroleum wells. Okay? It just means the pressure surface up there someplace. Okay? And the last thing, which is the dry well? Well, process of elimination says you drilled a little too low, you tried to slot in a shale, shame on you. Okay? So each of these wells tells you something about the potential and the geologic setting. Now I'm going to focus on 3 case studies with respect to Texas, the Houston area, San Antonio area, and Panhandle. And let's look at that Houston area first. But before we do, let's look at Texas and see where these aquifers are. If you look at the state of Texas, you can draw a line. Actually, if you look at the United States, you can draw a line more or less along the 100th meridian that separates areas that are basically humid from arid, from excess precipitation to evaporation greater than precipitation. It's got all sorts of implications in terms of agriculture, in terms of ecological diversity, but what we're interested in is what it means in terms of water resources. So let's look at the square, and we see that same range from over 56 inches a year to less than 8 inches a year in El Paso. So there's a lot of variation of rainfall within the state of Texas. And this also means there's a lot of variation in water issues in the state of Texas. Now you can draw a line that's basically I-35. And as we'll show in a moment, that's also more or less the Balcones Fault Zone. Seems odd, but we'll talk about why in a moment. And so most of the population, 80% of Texas, lives east of I-10. About half, a little over half the water use is from there, and about a third of water used for irrigation. On the other hand, that 20% of the population here uses 45% of the water and 85% of the irrigation. Fewer people, more water per person, and in particular for irrigation. And the reason, quite obviously, is it doesn't rain there much, and this is a rural agricultural region, so we're either going to irrigate for crops or for cattle. Okay, so this is, if you like, the problem for the state of Texas. So we're going to look at how that the availability of water for irrigation is controlled in large part by the distribution and availability of groundwater. So we're going to look at three areas. This is the Gulf Coast Aquifer, including Houston. We're going to look at this strip here, which is the Edwards Aquifer, including Austin and San Antonio. And then we're going to go up to Lubbock and Amarillo and look at the Ogallala, which by far is the largest aquifer in Texas. Okay, so let's look at the Gulf Coast Aquifer. And this is an isopac map or a map of equal thickness for sandstones, or sands, better said, containing fresh water. And if you look there, if I drew a little cross section through Houston, you'd find that in some areas we got over 1,000 feet of sand that's full of fresh water. So that's a good place to be if you're trying to get, it's okay. As long as it's not my pacemaker, I'm okay. So this is a huge aquifer, and let's see what it is stratigraphically. We basically have layers, slightly inclined, of unconsolidated sediments, sands and clays, I'm generalizing. And these down in this area are hundreds of thousands of years old, but they're still pretty young and relatively unconsolidated. And then we got a little sand here, which is Galveston Barrier Island. So the city of Houston, plus the Houston Ship Channel, for the longest time, was drilling and getting water from this aquifer. It was a confined aquifer, confined by these clays. Okay? Now, where did it get its water? Well, you have to go to Conroe and the woodlands to find sandy soil. You may actually see this change as you go north into the pines, and this is where the sandy soils are. And these sandy soils are the outcrop exposure of these sands at depth that are thick and have a lot of water. Okay. And now we've gone over this before, but it's important to reiterate. So this line here, what is that line? If this is the water table, what is the dotted line?
The level at which the water resides.
Absolutely. And what do we call that surface? The pressure surface, or the potentiometric surface. Okay? So we start pumping. The surface goes down. There's a cone of depression that is created in the pressure surface, just like there is in the unconfined aquifer, the water table. The problem here, though, is that we've set up a gradient where we're beginning to dewater the clays. We are actually deriving the water not just from compaction of the sands, but from compaction of the clays. So what that does, it generates a surface subsidence that is that subsidence bowl we talked about. We talked about the Brownwood Marsh and how it used to be the Brownwood subdivision, and we talked about how that lowering the potentiometric surface by pumping water out of that confined aquifer, we cause compaction of the overlying clay-rich sediments and a lot of subsidence. And that led to the creation of the Houston-Galveston area groundwater conservation something or other. I can't even remember the name now. But basically, that caused us to go off of groundwater onto surface water. And we also talked about the fact that now we're getting a big bowl out here where we're looking at the growth of Houston to the west in areas that are still on groundwater. Okay. So that's, if you like, that's the problem of Houston. The problem is we're being forced, for good reason, to go from groundwater to surface water, not because it's cheaper, it's actually more expensive, but because of the negative environmental consequences of subsidence associated with groundwater withdrawal. So let's look at the Edwards Aquifer for a second. I mentioned earlier that you see signs all over the area letting you know that you're in it, or you're entering it, or you're leaving it. So they're very strictly controlling the land use in that area. So let's look at the area here. Here is the Balcones Escarpment. And this line that I'm drawing is basically the Balcones Fault Zone, okay, with uplifted lower Cretaceous limestone forming the hill country and downdropped upper Cretaceous limestone and marls and shales and sands going all the way through the coastal plain to Houston. Okay. In fact, the youngest of those sediments of the coastal plain is the Gulf Coastal Aquifer. All right. Now, one of the things you might notice, we got some limestone quarries here because we've taken old limestone and uplifted it. So a lot of quarries, and we've got New Bronzeville. In fact, if we were to look at where the cities are, Del Rio to Waco and beyond, it's kind of interesting because these cities all seem to follow the Balcones Fault Zone. So either these cities were established by a series of geologists who were structural geologists by inclination and wanted to live near a major fault, or there's something else that was controlling the development of those cities. Okay. Well, several things, but first of all, the uplifted Cretaceous of the hill country is pretty good ranching land, but not good for much else. On the other hand, the areas on the downdrop side are very good lands for agriculture, for farming especially. So first of all, this fault has created the juxtaposition of two different economies, a ranching economy and a farming economy. In addition, these cities tend to be where rivers are crossing, so they represent conduits through which you could go from the coast up to the city. And then beyond here, it's getting kind of hard because you're getting in uplifted areas. And lastly, these are areas of naturally occurring springs. So we've got springs, San Marcos with Aquarina Springs, Austin with Barton Springs, San Antonio with Comal Springs, etc. So for a lot of reasons geographically, the Balcones Fault has been an important factor in how we've settled Texas. There are some of those artesian springs we're talking about. And so let's see, how did that happen geologically? What's the geologic story? Well, if you go back to San Antonio 120 million years ago, you see basically a series of mainly carbonate rocks, limestone, but some of them, like the Edwards, is a massive reefy limestone with a lot of holes because it's been dissolved. By the way, this is where a lot of the caves are, like natural bridges and the like. Okay, and then it's overlain by younger units that are less permeable. They tend to be more clay rich. Okay, about 30 million years ago, the Balcones Fault uplifted, and so we've got this high area that's eroding, and we've got this downdrop series of downdrop blocks along the Balcones Fault Zone, and this is where we are today. So the hill country, sometimes we call it the Edwards Plateau, is capped locally by this resistant but porous limestone, and then that same limestone is dropped successively farther down in the downdropped area of the coastal plain. Okay. Now, there's a band here where that Edwards limestone, although it's fault bound, is exposed to the surface. And it's connected to another band of Edwards limestone that is below the surface, overlain by that less permeable zone. So these are confined aquifers. So we've actually got an unconfined aquifer of the Edwards here, and then we've got confined aquifers or artesian aquifers farther down. Now notice we break it up. There's an artesian aquifer zone and then a bad water zone. This is not an aquifer. It's not because there's no water. It's not because it's not under pressure, but rather the water quality is too poor. So again, remember the definition of an aquifer is that it's got to be economically usable. Okay. So what is the source of the water here in this confined aquifer? Well, it's whatever water enters in the recharge zone. Okay. So this is a really important area to provide the artesian wells that are supplying not only springs, natural springs, but major municipal and agricultural users. Notice also that this potentiometric surface is controlled by the level of the water table in the recharge zone. Okay? So anything that you do in the recharge zone to lower the water table will also lower the potentiometric surface. And one of the things you really hate if you're using a confined aquifer, if you have a flowing artesian well, is for that pressure surface to drop below the ground. Because that means now you have to install pumps to get that water up. Okay. So let's look at a map for a second. The greenish portion of the Edwards Plateau that is hydrologically connected to the artesian zone. Okay? The only difference is in the artesian zone, that aquifer is confined. It's dropped below, so there's got to be a fault here, a series of faults, and there's got to be a fault here. Okay, so we have a fault-bound block of exposed Edwards. Now, we have another zone that I really didn't talk about called the catchment area. The catchment area is basically a series of connected watersheds bounded by a drainage divide that basically funnels water into and past the recharge area. Okay, so the water that actually gets into the recharge area is not just the rain that falls, but it's also the rain that falls in the catchment area that can at least potentially soak into the ground from the rivers. Okay. So both areas are important, both in terms of pollution, but also in terms of source of water. So one of the things you see as you get into the recharge zone, you'll see a whole series of little lakes and dams and holes, quite literally, where when it rains, water coming down, once it hits the recharge zone, it's diverted into a big pond, and what we call a recharge pond, to artificially recharge the groundwater. Okay. So this is an isothermal map. Remember, that's a map of equal rainfall that shows how much rain falls in the Edwards Plateau from about 22 to maybe 30 inches. And that pretty much is what controls the amount of water in the Edwards Plateau. Because anything beyond here, anything along here, doesn't matter. Actually, anything beyond here, because it can't get in the aquifer. So it's only the recharge zone and what feeds the recharge zone. Okay. Now the problem is that's average rainfall, and if we look at an interval from about 2003 to 2014, this is what we call a water deficit. Okay, where we're getting I forget the exact term, but basically we're getting less water than we need, and cumulatively we've had greater and greater deficit. Now this may be just inches below average, but now we're looking at a deficit of over 80 inches of rain. Now what that means is that the water table is dropping. In fact, if you go to San Antonio or Austin, in the paper every day, in the news, local news every day, there's what is the level of the Edwards Aquifer. I mean, it is literally something we follow daily. And it's very much controlled by how the water has been. And so just as the level of the lakes is influenced by drought, so too is the level of these aquifers. Okay. Now, the problem with the Edwards Aquifer, particularly from about San Marcos down, is that you had three different groups that were really interested in that water, all of whom wanted to get that water. One was San Antonio. San Antonio is the largest first of all, it's like the 10th largest city in the country, and it's the largest city to be completely reliant on groundwater. So that makes it unusual and unusually attached to the artesian zone, because these wells were not only the reason why the Spanish settled in San Antonio, but that's still where most of the water is obtained. But the other problem is, as you go south of San Antonio, you get into Uvalde and other areas where you've got a lot of farming communities and ranching communities. And again, their water is obtained mainly from the aquifer. And lastly, you've got a whole series of naturally occurring springs that are coming up under pressure that are occupied quite happily, thank you, by little fish and things, some of which are endangered species. Okay, so the Sierra Club comes in and says, who speaks for the endangered species? Well, we speak for the endangered species. So you got the Sierra Club, the city of San Antonio, and the farmers, and they're all arguing who gets the water. One of the reasons that's a problem is that if the water levels drop too low, not only do the artesian wells stop flowing, but the natural springs stop flowing. And so if you dry the springs, you wipe out the endangered species. So in 1993, actually until 96, after legal issues, there was the Edwards Aquifer Authority that was developed. And it basically was a water manager, or rather, it helped to manage the conflicting needs during times of drought. Because when it's not drought, everybody's happy. When there's drought and water levels are dropping, there's not enough water for all three constituencies. Okay, so if you look at the pumping that occurred from about 1947 up to 96, it was increasing, and then with the Edwards Aquifer system, it's been more or less constant. It's being managed. Okay, we'll just skip that. Now, we talked earlier about the way in which water is owned in the West, and we talked about the American rule or the English rule, and this is one of those cases where the American rule rules until it doesn't. And in this particular case, this is an example of the English rule where it's the beneficial use. And so the criteria that's used is that you have to maintain a minimum amount of water in the aquifer as expressed by a level of the potentiometric surface to keep the natural springs flowing. So first and foremost, save the pupfish. Secondly, then you got the farmers and the municipal users. And so one of the things that's happening is that San Antonio is being requested very strongly to get off of groundwater, or at least reduce their reliance on groundwater. Now remember, that's exactly what happened in Houston. For different reasons. Okay. Here, though, it's not as easy as in Houston, because Houston sits in that area where we got 40 plus inches of rain, 45 plus inches of rain a year. So we just tap into the San Jacinto River or tap into the Trinity River. Here, there's really not much to tap into. And so it's much harder for San Antonio to switch to surface water than it was for Houston. Okay. Right now, though, they're looking at actually building reservoirs farther down and then pumping the water back up. They say building reservoirs in areas where it rains more and then bringing it back up to San Antonio. So that's the issue that's going on right now in San Antonio and with the Edwards Aquifer. Now, the Ogallala Aquifer is one of perhaps the greatest national interest. It's also the largest in Texas. Covers most of the panhandle. And in reality, what we have is just a little piece, not an important piece, but a little piece of the entire Ogallala Aquifer that extends all the way up into Nebraska. Literally, it underlies almost all of Nebraska and then a little bit of South Dakota. Okay, and it is the largest aquifer in the United States. Now, the Ogallala Aquifer has been in the news the last couple of years. Anybody know why? The Keystone Pipeline. Okay, and it's going to go right across, rather right over the Ogallala Aquifer. And so the issue there, the environmental issue, at least the issue up front, is the fear of contamination of a really important aquifer by leakage. Now, I should also add that the Ogallala Aquifer is an unconfined aquifer. So it is much more susceptible to surface water pollution than a confined aquifer. Okay. Now, a second reason, an environmental issue, is that a lot of people just don't want to see us using Canadian heavy oil. And I won't say the groundwater leakage is a subterfuge, but it's a separate issue that probably could be solved, but it still would not address the underlying issue, which is continued reliance on heavy oil. And so sometimes our reasons for complaining about something, our issues, are more complicated than it would seem. But let's take it at face value that it is an important aquifer, and let's see, first of all, how it formed, and that is it was a large area of sediment that was shed off of the Rocky Mountains as a big ramp of sediment. It's then been largely eroded, and so here's that ramp that comes up. And the sediment is gravel and sand, unconsolidated deposits, and it is full of fresh water. Okay. The problem is that it's in an area now where it doesn't rain very much. There's about 24 inches of natural recharge. I'm focusing here on Texas, I think, but it's a good example in any case. And the natural discharge would be 24 inches. And so basically, this is the equilibrium input-output that allows you to have a stable water table. Okay. If you increase the recharge, the water table will rise. If you increase the discharge, the water table will drop. So this is before development. Now, though, we are pumping 830 units. Now, a lot of that goes back, but not nearly as much as we take back. So we are decreasing the units by 330 units, and now the natural discharge is down to 10. This is a long way of saying that we are depleting this aquifer. The aquifer is dropping because we are taking out more than is going back in. Okay. Here was the base in 1950. The base predicted in 2050 is that the aquifer will be completely dry. Now, that seems a bit extreme. Let's look at what's actually happened. If you look at the water table drop before development to 1940, we're looking at 100 to 150 feet of drop. Okay. The greatest drops through 1997 are actually sitting here in the Panhandle, okay, where we're looking at the percent thickness. Over half of the thickness of that water column is gone already. Okay, so we are pumping this water out faster than it's being recharged, and the way we refer to that basically is we are mining the groundwater. We're treating the groundwater like it's a non-renewable resource. Okay, we're taking it out faster than it can be renewed. Now, the other thing that's kind of interesting about that water itself is pretty old. We can actually date water. Remember I said the residence time of groundwater is very long. This aquifer was filled at a time in geologic history when it rained a lot more, which is to say the last ice age. So the water that we're pumping today is rain that fell 18,000 years ago when it rained a lot. So we have this water, if you like, in a bank account. but now we're taking it out faster than we're putting it back in. Not unlike fossil fuels. It's a very similar situation. Okay. Now, it's also a very serious problem because remember when we talked last time, Monday, about water in Texas, and one of the assumptions, one of the parts of the planned changes is that we will decrease our reliance on groundwater, and in particular we'll use less and less water for irrigation. Okay. Where's that water going to come from? Where's the water irrigation loss going to come from? To a large extent, it'll be in areas like this. Okay, and so the question is, how will this affect the state economy, but also how will it affect the regional and local economy? We're talking about trying to figure out how to reduce our reliance on irrigation in an area where it just doesn't rain enough. Well, you could go to dry land crops, which is what they did before they had these big wind turbines, or rather windmills, water wells. That's tough. You could increase conservation efforts, and there's a lot of work going there to reduce the loss of water by evaporation. Again, I'll just remind you that one of the things that will happen with irrigation is that we get increasingly salty soils. So this is a problem. Try to reduce the salt content. And there's no easy answer. There's no easy answer. One thought is to bring water from Oklahoma. Take water where it rains and bring it in, kind of like San Antonio would like to take water from down near the coast and bring it up. Except Oklahoma may have something to say about that. So now we're talking about interregional, actually interstate water transfers. Oh, and by the way, when we think about San Antonio taking surface water, that water that is being removed is water that's not going into the bays. Copano Bay, the bays around Corpus Christi, which means there's a significant issue with respect to water quality and environmental ecological consequences by reducing the water there. And so that is an issue that will have to be addressed as well. So we've got a lot of problems in the state of Texas. They are really problems that are seen everywhere. California is almost a mirror image of us worldwide, but they bring home this issue of water use and water availability. Okay. Now, and I haven't mentioned groundwater contamination through pollution. Okay, or if I have, just in passing. Basically, when you have a degradation of water quality, as measured by some kind of criteria, biological, chemical, physical, and it's anything that when in excess could be harmful to a desirable living organism. I like that. Undesirable organisms we don't like. Okay, that's how we get rid of them. But if it's desirable, we don't want to harm it. Okay, so we've got two types of pollution, and that would be air, surface water, groundwater, and that is a point source and a non-point source. Okay, it's the easiest to think about air pollution. A point source might be a refinery. A non-point source might be cars. A highway could be a linear non-point source. A farm area might be an area non-point source. Okay, so we have to look at where the pollutant, whatever it is and how it's getting into the groundwater in our specific case. Well, let's see. Here's some point sources. Maybe a landfill, coal mine, non-points, maybe a septic tank, although those are so small and so many of them that sometimes we treat them as a non-point source. A non-point source would be agricultural areas here. Okay. Oil and gas wells would be a point source. Road salt would be a linear non-point source. Again, septic tanks could be considered either, depending on how you address the problem. Okay. Well, let's look at something that is an issue in coastal cities, and Galveston being one, and that is where the pollutant is too much salt water. Okay. Seawater is about 33,000 milligrams per liter. Drink water is about 250 or less. The good news is that fresh water is less dense than salt water, so that when we look at sea level, there is a zone is represented by fresh water floating on top of salt water. So it's a lens. It's a freshwater lens of fresh water. Now, the elevation of this diffuse base is actually dependent on the elevation of the water above sea level. So the more water you pile up, the more you compress that particular contact and you thicken that freshwater wedge. The problem comes when you pump that water table and you lower the amount of fresh water that's on top of the salt water. By lowering it, you allow the salt water to rise, and it can, in fact, intercept the well you're pumping. So we have at the surface what we call a cone of depression, but at the saltwater interface, we have a cone of ascension, where we're drawing up the salt water. And once you do that, then you begin to pump salt water, and you either have a non-potable water or you can't use it for irrigation, etc. So this is a significant issue in coastal areas. Okay. I might add, the way you can prevent that is sometimes have an injection well along the coast to have a barrier. Okay. But often the way you prevent it is just quit pumping. Okay. Now, let's look at some more noxious types of pollutants. And in particular, there's a group of pollutants that are called non-aqueous phase liquids. Okay. That is to say, they're not water, but they're liquid. They're usually organic or hydrocarbon based. Okay. And we typically subdivide them based on their density. Are they relatively light, especially lighter than water, or are they relatively dense or heavy? So we have light naples and dense naples. Okay. Now a light napple would be something like gasoline. So gasoline would be a type of pollutant that floats on top of the water, and it also floats on top of the water table. Okay. And when the water table fluctuates up and down, you take that gasoline and you smear it onto the particles that are within the vadose zone. So it not only pollutes that little thin strip where the water table is at any one time, but because of fluctuations, it can pollute a significant width or thickness. Okay. So here we have the most typical source, a leaking underground storage tank. It comes down as a fluid. It begins to disperse a little bit as dissolved hydrocarbons, and it goes down vertically until it hits the water table, and it begins to migrate. Okay. And it's floating right here. And notice the smear zone. This is the zone where the water table fluctuates. So we've got a zone that's just about like this. And here we've got some of those hydrocarbons in solution that are beginning to both dilute and disperse, so that the polluted plume, the hydrocarbon plume, is heading down the water table, or rather down the aquifer, initially at the surface and then gradually dropping down a little bit in a direction and in a velocity that's determined by the gradient of the water table. Okay. Now, because these are largely the result of leaking underground storage tanks, this was the savior for unemployed geologists in about 1980, when legislation was passed and money provided to remediate this, to replace these old tanks with new tanks. And so we had the rise of filling station geologists, where we drilled a bunch of holes and we figured out where the pollution was, and we replaced these tanks. Okay, that money dried up. The geologists, some went back to oil and gas. Now some of that money, up until this most recent administration, was being put back into remediation. We don't know what will be available in the future. Okay. But underground storage tanks were a major source of pollution and in terms of employment. There's another type of hydrocarbons that are more dense, and they tend to sink to the bottom of the aquifer. And one of the more common ones are solvents that are used in dry cleaning. Dry cleaning outlets are one of our major pollutants. Okay. And so there again, these DNAPLs are working their way down. Here's the water table. Okay. And they're beginning to seep down that upper unconfined aquifer, and they basically ride along the base because they're more dense. Of course, they're dispersing and diffusing, but we also have a problem in that these aquicludes sometimes have holes. And so these aquicludes, which are better said aquicards, can also be breached, and when they breach, then we get these dense NAPLs, not only polluting a large area of the unconfined aquifer, but the confined aquifer as well. And this is kind of a worst case scenario. Okay. And of course, it's a very different type of pollution than we get with the light source. Okay. Okay, another point source would be municipal landfills. Okay. Now, the good news is that we've taken a lot of efforts to minimize the amount of groundwater pollution from modern landfills, which is rather different than when it was some time ago, where a landfill was typically sited where you had an old sand pit. So, of course, you've got a hole in the ground already there. You dump bad stuff in it. Oh, the fact that that's the recharge area for your groundwater, oops, my bad. So as they went away from that, the first thing they started doing is trying to find geologic areas where they're clay rich. So first of all, forget the sands and sandstones, focus on clays and slaystones. Secondly, line the base of that particular landfill with something impermeable like plastic and clay, and then intercept any leachate that forms, because leachate always forms, by a series of drains, and you pump it to be produced. And then you, by the way, monitor to make sure that there isn't a leak. Okay. So might look something like this. Here's the trash. Here's the liner. Now, we've actually put a clay cap on top of it too, to reduce infiltration. We want to minimize the water getting in there, but there's always going to be some water, so there'll always be some leachate that results from the decay of the modern garbage, and so the liquid portion of that is collected, brought out, and treated. The gaseous portion is methane. One of the byproducts of modern landfills is methane production, and so that's coming out here, and so you're trying to recover that. In old landfills, it might come out by filling your neighbor's basement and your neighbor's house blows up. So this was a major problem until we started capturing it and treating it. Okay. This is just another example, but this one shows also our monitoring wells. So the other thing we do is we make sure, here's some drains, both above and below, but we make sure that if leachate does end up being produced, we can intercept it here, but also recognize when it's getting to the water table. Now, notice there's two wells here. There's a well down here that's below the water table, and a well up here that is in the vadose zone, and that is because we can also have pollution of the vadose zone as well. Okay, so we need to monitor both. Okay, notice also that in terms of the spatial distribution of these monitoring wells, they are predominantly going to be in the downflow direction. And how do we know that? By contouring the water table. So if we know the water table, like we did last time, we can generate an area where it's likely to be going, and that's where we put the bulk of our monitors, but we also will have some in other areas because we know that water tables can change, particularly if, say, somebody started pumping over here. So we might change the direction of flow. Okay. A big source of potential groundwater pollution is septic tank systems. About 25% of the households in the U.S. still use septic tanks, and they are basically designed to remove a variety of things. And the way they work is basically the water comes into a large holding tank where the solids precipitate out or drop out, and then there's a perforated tube that comes out, and then the liquid portion is drained out through a series of slotted PVC tubes, and the idea is that it's dispersed and then it does gradually drain into the groundwater, but the intent is that through filtration and through distance it cleans itself up. Okay. Now here in the tank itself, there's a series of anaerobic bacteria that break down the solid waste, and then the liquid comes out in here into the soil. And the hope is that the bacterial action within the soil will take care of most of it. Notice there's a vent pipe here for any gases that might escape. Usually that's not included, but it's a good idea. Okay. So this is what it looks like in map and plan view, and here's the water table here. So what you don't want to do is have it too close to the water table. That's the first thing. You want a significant distance below that drain pipe for the water table. If the water table is too high, it's not going to work. Okay. You also don't want it too close to your neighbor's well. And so there are criteria that say how far it has to be from the nearest well. Okay, so there's a variety of criteria that are used to determine whether or not you can put one in. The other thing is what type of sediment is above the water table. Is it impermeable or is it permeable? You want it to be slightly permeable. You don't want it to back up, but you don't want it so permeable that it'll just soak through without retardation. Yes, ma'am.
That rainfall, is that just filtered sewer?
Yep.
Water?
Yep. It's the same thing that would go into a sewage treatment plant in the city. Okay. And it works as long as you've got some distance and time for it to filter out and reduce some of the noxious material. And of course, it does. The solids have to be pumped out periodically. It's not a job I'd like. The septic sludge. Yes.
How about the chemicals that are put into the septic tank? Does that also?
Yeah. Those are if you like, the anaerobic bacteria that are designed to break this up. So the good news is the sludge is a very reduced amount of material. It's not particularly obnoxious, but it's got to be treated. Okay, so here's some of the problems you have. Failure of a septic tank means the water starts to back up and spill over the surface. Never a good thing. Poor soil drainage. Okay, it's just not permeable enough. So that's why you have to run a permeability test with a test pit hole before they'll let you put it in. Okay. The high water table. Yeah, if you've got if you're too close to the water table, and especially if it rises, that won't work. So it used to be, well, let me rephrase that. The most recent guidelines requires at least 4 feet above any impermeable surface of the water table. Okay, it used to be 2 feet. So you're seeing guidelines changing. And those guidelines, by the way, are typically city or county guidelines, so they'll vary from place to place. Okay? Yeah, all right, yes. Okay, so here we have a leaking underground, not leaking, let's assume for a second this isn't so much leakage from a tank, but from the drain field. Some of it still can get into the groundwater, and as it flows in, this plume is supposed to be cleaning itself. Okay, you are updrift, not a problem, until your neighbor starts to pump more, and now you are pumping your own sewage. Never a happy homeowner here, and the irony is that the septic tank and the well were situated in a place which is relatively safe until we began to alter that particular area. Okay, so this is just an example of the water overflowing. It's in the well line. The lateral lines are those lines that go out. Here we actually have the septic tank itself exposed due to erosion. Obviously, septic tanks are used a lot in coastal areas, beach houses, and so that's one of the problems we see in erosion is failure of septic tanks. Okay, now in part because of that, and in part because there are areas that don't meet the criteria necessary for a septic tank, more and more you're seeing rural areas or areas that do not have public water treatment using aerobic treatment systems, ATS. And so basically you're having water that comes into a series of tanks, a pre-treatment tank, and then it's aerated, and then it's clarified, and then it's chlorinated, and then it's pumped out. Okay. So literally, it is a local residential sewage treatment plant. Okay. And so you're both aerobically and chemically treating it, and then you're spraying it out. You quite literally have a series of sprinklers that spray the water out, and in this case it looks like it's very nice because it is giving you a nice lawn. Okay. There are some advantages to this. I'm going to not read them, and you can look at them only if you're interested, but I'll tell you that some of the big advantages, you can put them almost anywhere, particularly areas that are unsuitable for septic tank systems. You can have a smaller area, but the disadvantage is that they're expensive, they require electricity and a lot of maintenance, and the other thing is they can smell. You can sometimes smell an area that's being sprinkled with this wastewater, and yeah, that may be a mechanical breakdown, but it happens. Okay, so we've identified a problem. We've got a leaking point source. So what are the steps we go through as environmental scientists or engineers? Well, first of all, we got to discover the source and determine what is it. What do we know about the source? What kind of material is being leaked and where is it? Second thing is to remove the source. Let's say a tank. We got to remove the source before we do anything else. Okay, and it may also mean removing contaminated soil. Okay, then you've still got this contaminated water. So you got to figure out, how do we remove the contaminated water? Well, we need to do a site characterization. We need to know what are the geologic and hydrologic properties of that contaminated aquifer. So these are some of the questions we would ask. What is the extent of the aquifer? What's the physical properties of the aquifer? Things like hydraulic, that should be conductivity, rock type, pore size, etc. Location and characteristic of the aquitards. How about chemical properties of the aquifer? And by that, I mean, what is the aquifer quality upstream? That is the before. So what are we trying to get it back to? In some cases, what gases are dissolved in the aquifer? We've got some dissolved sulfur, for example, in naturally occurring aquifers. So we need to know that as well. So once you've kind of figured out what the site is, you've got to figure out where the area has been contaminated, the impact evaluation. So how do you do that? Monitoring wells. So you put a whole series of monitoring wells to calculate where the contaminants are and how fast they're moving. Now, ideally, you would make a model, and what this model will do is model the flow, not only, well, first of all, it will model the aquifer and aquatards, then it will model the fluid input, both with respect to the water and the contaminant. And so we do that as a groundwater hydrologist, and we do it in part to figure out where we're going to have to add additional monitors to completely determine the plume. And lastly, remediation. Now we got to remove or at least contain that contaminated plume within the aquifer. Okay. So what are some of the ways we can take care of this groundwater pollution? Well, there's a variety of methods. These are just some. But let's take the one that we used to use a lot, and that is we would pump out the water, put it in a treatment facility, typically on site, and then discharge it into a creek. Okay. The problem is, well, there's several problems, but one of them is this can take forever. And it rarely removes all the contamination. There's some contaminants in particular that stick to the soil, stick to the rocks. They're absorbed and it's hard to get them off. You can't get liquid naphthalene out very well, and it's very costly. Okay, so we're going to other things, and one of the things now that's being used is we call air sparging and soil vapor extraction. Here's a contaminated aquifer, okay, and we are putting air in here and a variety of other things, and we're getting that soil vapor to try to get not only the contaminated aquifer, but also some of the soil in the vapor phase, in the vadose phase, out as we've got this air bubbles coming up and then coming out through here. Then we treat it with activated charcoal so that we can get rid of the volatile organic compounds that way. Okay, it's got some disadvantages too, so we'll leave it at that. One of the neat things that I've never seen used, but literally put in a barrier. Here you've got volatile organic carbons coming down. They hit this permeable reactive barrier. What it is, it's basically a big filter that treats by removing the organic carbons and then pump it out. Okay, so that's kind of neat. Okay, it as you can imagine, it's kind of expensive, but there are places where that might use. And by the way, that soil that we can't get the stuff out, we literally have to remove the soil. And so you've got to remove it and treat it. And there's a variety of things you have to do, but basically it's a hassle. Okay. And so this is a little flow chart that talks about all the different things that you've got to do to that soil before you can do anything with it. And this is just out of yesterday's paper. Chevron talks about property cleanup. They're drilling 80 monitor wells, and they are removing the soil of their property that their research lab on Forness, just outside the Loop in Bel Air, before they can sell it. And there's all sorts of contaminants there, including radioactive contaminants because of well testing. And The soil is leading. Within the water, tests suggest that the level of contamination is not too contaminated to be a health problem. So they're not doing anything. They're not doing any remediation, but what they're doing is monitoring. So they're monitoring the location and amount to decide what, if anything, to be done later. And this is a huge issue because of liability. Whoever buys this property is going to be buying a significant portion of the liability should serious problems happen later. Okay. Here we've got some soil that was contaminated by petroleum and is being treated by bioremediation cells. Well, that's kind of interesting. What the heck is that? Well, bioremediation can be a variety of things, but here's one example where literally the root systems of plants are picking up contaminants and deleting them into the air more clean or in forms that are less serious. And that is, remember, the purpose of these riparian borders, particularly with respect to nitrate fertilizers, to use the trees as remediation. But in reality, we often will add organisms that will treat the contaminants with surface pollution and oil spills. Bioremediation is a major role in terms of letting microorganisms, bacteria, eat up the pollutants. Okay, so it's effective, and in some cases can actually replace mechanical cleanups. Okay, here we're looking at it at different scales. At the microscopic scale, here we're beginning to see the mesoscopic and macroscopic. We're injecting nutrients and in some cases the actual organisms, although sometimes we just feed the organisms that are there. That's kind of what we do with the septic tank. We throw in Rid-X and the natural bacteria just go crazy and they get collected. And so enhanced bioremediation is a major issue where we're basically using natural bacteria and encouraging to break down contaminants like trichloroethylene and carbon dioxide, etc. So this is especially useful. And this is just the idea of what happens when you've got a contaminated plume and a whole series of things that reduce the degree of contamination by various processes. So the contaminant is a hydrocarbon, and by a series of different processes, sulfate reduction, iron reduction, aerobic degradation, we end up with a relatively clean product. Okay. One of the issues we have, and the reality is sometimes we can't clean up the water. And so what do we do with it? Well, we can inject it. In fact, we might do that simply because it's cheaper. If you got a very large volume of contaminated water, like salt water maybe, where you've been using it to artificially drive or increase the production of a well field. It comes back up, it's contaminated, you just got a lot of salt, you can't put it back in the river. What do? You inject it, and you inject it down here into an area that is separated from your potable water, your fresh water. Okay? Now, it's separated by a series of aquitars or aquifluids. Okay? But as we know, they leak. And so if you do inject it down here, first of all, you want to inject it into something that's relatively permeable because you want to basically use that porosity to store your contaminants. You better have a series of monitoring wells to make sure that there's no leakage. And so at each of the different levels around that injection well, you want monitoring wells. Now, as you also know by now, this can result in earthquakes. We see that with fracking, large volumes of water that are being injected into deep reservoirs If they're injected too fast, they can decrease the shear strength by increasing the pore pressures and therefore cause earthquakes. Okay. Some of the polluted areas, particularly areas that were polluted in the 50s and before, have some really obnoxious pollutants that have been polluting for a long time. They may be chemical waste or even radioactive waste stored in barrels or buried in unlined areas or unlined storage lagoons. And these are sometimes called the brownfields. These are areas which often were then covered and then developed, much to the chagrin of subdivisions that were put on top of them. And so as a result, we've got a series of major legislative regulation, federal regulations, to try to deal with this. And one of them in particular was the one in 1980, which did, among other things, not only, which basically created CERCLA, which is the Superfund site. And then in 84, underground leaking storage tanks. And then most recently, the American Recovery and Reinvestment Act, which more or less, among other things, put money back into removal of contaminated water sites. Now the Superfund sites, RECRA was the first, okay, 1976. This gave EPA the authority to control hazardous waste. They say from cradle to grave. That means from generation to final disposition. Okay. In 84, they expanded that, included some enforcement authorities, and started a program for removing leaky underground storage. Now in 80, though, the Superfund side, this slide is out of order, basically it created a tax of big companies that says, okay, a lot of times we don't know who's liable, or the people that are liable, they can't afford to clean it up. And so everybody's going to get together, put together a general fund, and we're going to use that money to remediate these Superfund sites. And there's a lot of them. They're especially abundant in the Northwest, but we got a lot of them in Texas and scattered around as well. These are very expensive areas to remediate, and they are highly polluted. And they basically are so polluted they cannot be used for anything else. And the biggest problem is just containing the much less dealing with remediation. So it's mainly groundwater impact, drinking water and soil, and even surface water impact, huge, and soil, even air impact and human health impact. So these are extremely contaminated things, from heavy metals to radioactive waste. Okay. For those sites, or for sites that you want to create new for this level of waste, you really have a task set out for you. But basically, again, if you look at this, it kind of looks like a municipal waste landfill on steroids. It basically is a high level to contain the waste, to treat it, etc. Okay. This is the most recent one, basically money to clean up contaminated waste and must restore. As part of the federal stimulus, most likely that's going to be cut, but because that's part of the money cut for EPA. So we'll see what happens in the future with this particular issue. And that's it. I'll put out new notes tomorrow.